This is lesson number 5 of the quantum mechanics mini lecture series, black body radiation part 2. So I talked about in the previous video about a black body. What is it? Well, it's something which completely absorbs all electromagnetic radiation falling on it, right? An example of that is a cavity, let's say with a small hole. Anything coming into it gets absorbed by the walls of the cavity and gets re-emitted, starts bouncing around. 1896, German physicist Wilhelm Wien, I don't know how you pronounce it, put together a sophisticated cavity. So he made a more sophisticated cavity, and he measured the radiation near the infrared, okay, and into the violet part of the spectrum, the electromagnetic spectrum. Okay, got a series of curves, as I showed you before. Okay, each has got a peak at a different position. Frequency, let's say, is at the bottom here, intensity is here. So intensity is the color. As I mentioned before, the intensity, the color of the radiation observed in the lab was proportional to the frequency of electromagnetic radiation. So this one's got a higher frequency than, let's say, this one. Okay, it's further along here. These are called radiation curves. Okay, and it was one of the central problems of theoretical physics in the 1890s. And at the time, classical physics, I should say, was the go-to, okay, method of explaining physical phenomena. And physicists used the idea of electromagnetic waves. Okay, electromagnetic waves were thought to bounce around the inside of the cavity. Okay, waves. So Wien actually derived the formula, and it only worked at high frequencies. Okay, for high frequencies of the spectrum that he was looking at. And then English physicists Lord Rayleigh and Sir James Jeans, they also used electromagnetic waves in their theoretical explanation and to explain what was happening. And their theory is now called the Rayleigh-Jeans law. Okay, and this actually worked. It only worked at low frequencies. Okay, in contrast to the Wien formula, the Wien law, formula/law. Okay, which was a real shock, and physicists at the time didn't know what was happening. And what was more shocking was that the Rayleigh-Jeans law predicted infinite intensity. Okay, for the UV region of the spectrum and beyond. Okay, so it worked at low frequencies. Anything above that didn't really work. Okay, this was dubbed the ultraviolet catastrophe, the UV catastrophe. And I'll draw a nice sketch illustrating this as best I can. Here's a graph, okay? Let's call this frequency, going along this way. Let's call this intensity. Let's suppose we did an experiment. We got these data results, these experimental points, data points, I should say. Okay, like a curve. So the Rayleigh-Jeans law worked at low frequencies, but then diverged, exploded at higher frequencies. Rayleigh-Jeans, okay? Frequencies going towards the right of the x-axis, increasing in size. The Wien law worked great at high frequencies, but at low frequencies started to also diverge. Diverge means to spread out, to disagree. Okay, so infrared's around here, low frequencies, ultraviolet's around here, high frequencies, okay? And this was one of the central issues of classical physics in the late 19th century. And this resulted in what's called the birth of quantum mechanics, a new field of physics. And I'll explain this in the next video, but this was sort of the driver of the need for a new theory, completely new realm of physics. Okay, you've got the ultraviolet catastrophe and you've got the Wien displacement, the Wien law, both failing at particular regions, and something was needed in order to have a perfect match with the experimental data. And we shall see this in the next video.